Hello, I'm for Denison, and I'll tell you a little bit about some of the research that's going on in my lab. So crops need nitrogen, but fertilizers pollute. So we're hoping to increase the net benefits from symbiosis, either by increasing the nitrogen that crops get from symbiotic bacteria or by decreasing the cost. Now, the bacteria live in these root nodules and they convert nitrogen gas from the atmosphere into ammonia, which they give to the plant. But there is a cost to the plant for this hydrogen and electrons basically coming from carbohydrate. So those costs, there are really two costs. There's the cost of making the nodules in the first place, and we're actually using photos taken of root systems and an artificial intelligence system that identifies nodules to measure those costs. And then there's a cost of operating the nodules. It's basically the respiration that the nodules are doing. And that's a bit tricky to explain in a short talk. But basically the slope of this line, this is the benefit that the plant gets and the respiration cost. And so recently we looked at a mutant that doesn't make the lipid PHB that the wild type rhizobia make. And that, of course, requires diverting resources from nitrogen fixation. So it's not surprising that both in terms of how much shoot growth you got relative to nodule weight and in terms of how much nitrogen was fixed relative to respiration, by both criteria, the mutant without the PHB was more efficient. But the PHB is beneficial to the rhizobia. It can allow them to reproduce even if they don't have an external food source of carbon. And in recent field work by Catherine Mueller, she found that as the rhizobia in the soil went longer and longer without a host crop, the strains that had hoarded more polyhydroxybutyrate at PHB during symbiosis became increasingly predominant. So they were diverting resources to PHB that reduced the benefits to the plant, but it was beneficial to the rhizobia in terms of long-term survival. So we can't just inoculate plants with a PHB knockout mutant and expect those strains to survive unless the host plants actually impose counter selection that favors more beneficial strains. And that's sort of what we're working on. Here you can see alfalfa nodules that had a nitrogen fixing strain. They grew normally and the rhizobia inside were able to reproduce. But when Ryoko Ono, now a professor at UC Santa Barbara, prevented them from fixing nitrogen, that stopped their growth and reproduction. And you can see this lower reproduction for alfalfa, pea, and soybean in all cases when the rhizobia didn't fix nitrogen. But those were cases when they didn't provide any nitrogen at all. What about mediocre rhizobia that provide nitrogen at, say, half of the normal or half of the ideal rate? Well, Toby Keers, now a professor in Amsterdam, looked at that. And sure enough, if the rhizobia fixed very little nitrogen or none at all, then they reproduce less than the rhizobia that were fixing at full rate. This scale here is the amount of rhizobia reproduction, and this is the amount of nitrogen fixation. But rhizobia that were putting half of their energy into their own reproduction rather than nitrogen fixation, the plant apparently didn't notice and they still reproduced. So the question is, can we find plant varieties of soybean or alfalfa or clover that have stricter sanctions and that only allow the very best rhizobia in their nodules to reproduce and bequeath those highly efficient rhizobia to future crops grown on the same soil? That's basically what I'm working on now. And thank you for your